Hello everyone. Welcome back if you were at the 3D printer panel. The goal of this talk will be to go over everything you would need to know, well, basically to get you started on everything you would need to know to build a nuclear apparatus in your garage or basement. So it will be an interesting talk, hopefully. And again, if you have any questions, feel free to blurt them out during the middle of the presentation. Sorry?
Can you build it in space?
So yeah, it's pretty cool that we had a talk that addressed fusion in space just before that, and I certainly have a lot of interest overlap with the talk speaker just before me. So we can talk about potential applications for space travel throughout this presentation, definitely. But pretty much everything presented here is not necessarily aimed at interstellar travel or power production. It's more as a learning exercise and to make neat stuff, which is why I sort of got started with all of this. If you want to have the slides on your smartphone, you can scan this QR code. I'm sure the slides will be, I can put the slides up on the PhreakNIC website after this, but see if this works. It should take you to the Google Doc. Hopefully it's not deprecated by now. Yeah. You're all owned.
Take a photo of everybody taking a photo.
Yeah. I started using these at DragonCon this year, and there was a panel we did that did not have a projector, and I ended up really being thankful for the fact that I had QR codes, because I handed it to one person, and then they scanned it, and then people kept scanning it, and we had everyone in the room with smartphones and tablets with presentations, so you never know when this will come in handy. Has anyone had success with this? Is it still working? Okay, cool beans. Excellent. Also, on that first slide, I've got my email address and my website. My website has a lot of contact information for me, so if you ever have any questions or want to get a hold of me, or you're building a reactor and you need advice or something like that, feel free to email me. All right, this is pretty great. Onwards and upwards. If you need to get the QR code, just get it from a neighbor. So this is goes without saying, but most of the stuff that I'm presenting can be harmful, if not fatal, if used improperly. I don't know legal regulations for...
How many times have you died and come back alive?
4 now, actually. Long story, we can talk about it later. It's a good icebreaker. So, yeah, know your local regulations for radiation appliances, x-rays, things like that before you go building something. Always use discretion on how you're advertising, what you're doing, and so on and so forth. Fortunately, most of the stuff that I do is sort of within a regime that is mostly legal and no one really cares. So if you were here earlier, you kind of already know who I am. If not, I'm a computer science student at Georgia Tech. I like building things. That's what I do. Actually, I do have an intro slide, same one from my 3D printer panel. But I'm president of an awesome place at Georgia Tech called the Invention Studio. I do research for the National Oceanic and Atmospheric Association and the Contextual Computing Group at Tech. And I also like to eat ramen and sushi. If you didn't get this from the talk before, or you haven't had a bit of physics in a while, this is basically all the physics you're going to need for this talk. But essentially, how I started all of this, I was really in middle school when I started getting an interest in doing atomic things, and had very little physics knowledge, and used this as a mechanism to teach myself, electricity and magnetism, radiation physics, all of that. And this is really all you really need to know. There are atoms and there are isotopes, and you can make them into ions. There are neutrons, protons, and electrons. And for all of this talk, pretty much all of the particle physics that we'll be doing is sort of on the atomic level and not so much the subatomic level. Although neutrons do play a large part in a lot of the fusion stuff that I'll be talking about. The neat thing about atoms that always mystified me is when someone said, okay, well, we're doing this, we have a nuclear experiment or a particle accelerator or a nuclear reactor. And as a kid, I was like, okay, well, atoms are so small, how are they actually manipulating them? And the great thing is that once you have them ionized, you can use electric fields or magnetic fields to do neat things with them. And pretty much everything in this presentation will be to that effect, taking charged particles and making them do our bidding with magnetic or electric fields. Why would you ever do this? Who possibly could want to build some sort of nuclear thing that could kill you in your garage? And the short answer is because it's really awesome and very pretty sometimes. The way the universe works is often incredibly elegant to a surprising degree. And I found just kind of beauty in particle physics and things that you can make using magnetic fields and charged particles and electric fields. Both of these pictures are from particle accelerators that friends of mine have constructed. The lower right one is from a cyclotron that was constructed by Timothy Keith, who is a professor at Rutgers. They made the cyclotron from scratch. It's a 12-inch cyclotron within a electromagnet that has about a 2 Tesla magnetic field, which is an extremely powerful magnet. And what you see here is actually a phosphor screen being slid in and out of the beam line. And this is a long exposure photograph, so you can kind of see the oscillations of the beam through the phosphor screen. The other is a ion beam going into a culmination lens. And this is actually a deuterium beam, and you can tell that because of the purple glow. This is from a beam on target fusion apparatus that Carl Willis has constructed. He's another friend of mine. The neat thing about this is there's still real science to be done, and particle physics and nuclear engineering and electricity and magnetism that can be done in your garage. And I think in an era where a lot of people are doing science, and we've been doing atomic science for a while now, it's kind of neat to think that I can walk into my garage and do something that maybe no one has done before. And I can do it cheaper and quicker than most other people can. One of the things that I think is really important for fusion is that we're building these really big reactors like ITER and NIF, the National Ignition Facility, but they take 30 years to build and $20 billion, and only a very small percentage of people in the physics community actually get to do an experiment on them. With a lot of the apparatus that I'm going to discuss right now, they can be built under $10,000 or $5,000, or really as cheap as you are good at finding things on eBay. And the implication of that is just about anyone who is interested in these fields of study can build their own and do whatever they want with it. So even if you're generating unsuccessful tests all the time, that's still a lot of data that could possibly be used to make some conclusions. That's kind of a big assumption, but I'm of the belief that distributed research on many, many systems might lead to some positive data. Again, it's an opportunity to learn this. Yeah, go for it.
Whoa, 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 whoa. Whoa, Chad. Whoa, you just advocated me going back to the garage and doing my nuclear research, and it was going to help. How am I publishing this where it will be a positive impact on the world?
Yeah, so we have a community online.
I'm going back to the garage and doing some shit, but just tell me how it's going to be an impact on the world when I get there.
By sharing it with other people who are also doing these same things. The neat thing about this is whoever who wants to can go and build these things. But there are also people in this community who have PhDs and who are licensed by the Nuclear Regulatory Commission or work at national labs and things like this. And when we're all willing to share information with each other, sometimes it can work its way up channels that have publishing power to make papers to put in scientific journals, if that's what you're all about. Again, the internet is our friend in this scenario and bringing this entire community together. We have a website called fuser.net, which is a huge forum. And I've personally been a part of several experiments where one person has done one thing and we said, okay, well, we've got 3 more systems around the United States that are almost identical to mine. Can we put this experiment into those and verify the results? So the sheer number of people that are doing this, and if that number ever increases, is really great to build a network of people who can do the same thing. And if enough of us do it on the web, we have enough of an impact to really make a wave. Especially with how fast popular media will pick up a story about something nuclear or fusion these days. Lockheed Martin. It's pretty easy to get a press release about fusion out on the interwebs. If you're actually doing this at a university, it's kind of difficult to jump through all the red tape with on-campus Nuclear Regulatory Commission and things like that. But the internet is the answer to your question, if that's decent enough for you. We can talk at length about that later.
Dr. Johnson brought up the Lockheed Martin story. Do you believe it?
So, Lockheed Martin. Fusion as on an experimental level has started out basically from the beginning with two kind of not too different from like a fluorescent light bulb, right? Imagine that you have plasma and Russian scientists were doing what's called pinch fusion, where they had a magnetic coil in the center and they could energize that magnetic coil and squeeze the plasma together and make it fuse. They noted that you could make a magnetic field down the entire length of the plasma, have a very hot plasma that's in thermodynamic equilibrium, which means that everything in the tube is really, really hot. And you could make the whole thing fuse. However, you were losing a ton of energy at the ends of the tubes. And when you're operating in thermodynamic equilibrium, any energy loss is going to hurt you a lot when you're running into ends of tubes. So the Russians, being as clever as they were at the time, said, oh, well, if the tube ends are what are hurting us so much, let's just connect the tube together and we have the torus. One of my favorite physicists and fusion researchers, still to this day, his name was Bussard, Dr. Bussard, and he's done a lot of space applications for fusion. He always used to say the only reasons that the Russians gave us the toroid as technology, to public domain, sort of, was because they knew no one else would be able to ever make it work. I think now ITER is getting close enough that we may actually see it break even, but as the saying goes, fusion is 20 years away and always will be. That's what a lot of the skeptics always say. So with Lockheed Martin, you still kind of have the same issue. If they have perfected magnetic mirrors, so apparatus for the ends of the tube to reflect the plasma back into itself and into the central beam without losing any or losing a very small amount of thermal energy from the plasma, sure, it may be working, or it might work. It's very odd for me to see, though, a release about a fusion experiment with like no data whatsoever to sort of back it up. I mean, even NIF is better at publicizing their results than what Lockheed Martin has done. But that's my personal opinion. There may be differing opinions in the room, and we can certainly talk about it after the presentation as well. But that's just my beliefs. It's cool to see people talking about fusion in the media anytime, though, because it's usually positive press, and I think any positive press for nuclear is good. Neutrons are awesome. You can get lots of those from Farnsworth fusers and particle accelerators. And again, the concept of knowing that you can take fundamental building blocks of the universe and smash them together and get neat stuff like neutrons out of them is pretty cool. So as far as what you can do as a nuclear reactor technology in your garage, there are a couple of options if this is the path you're considering going down. So we have Farnsworth fusers, which is what I've built so far. You can also make neutron sources out of just elemental neutron sources, call it that. So you can take americium from, it's pretty commonly known, you can get americium from smoke detectors. You have to get a whole bunch of it, wrap it in beryllium, and then you have a neutron source. This option is not very legal whatsoever, and interested parties are cautioned against this method. A lot of universities, though, back in the day, the Atomic Energy Commission made a bunch of plutonium, beryllium, neutron sources for universities. North Georgia College has one of these that they use for calibrating their neutron detectors, and we got to play around with it a little bit in school.
We're actually University of North Georgia now.
I only say this
Oh.
because I was against the state, now we've merged with them, and now we're a university.
Do you know Dr. Spraker?
I'm familiar with the committee he's on.
Okay,
but
yeah.
that's-
Thank you for the correction. I'll try to keep that in mind. So,
It was just a recent consolidation.
yeah. So, so they have one. It's pretty neat. These are really cool. I have a friend who has made one of these americium beryllium sources. He's actually a licensed nuclear regulatory officer, so he has some, or nuclear safety officer, so he has some clearances and liberty to do some experiments that most of the rest of us don't really have the courage to publicize doing. But he has an americium beryllium neutron source that he's able to put inside of a high-density polyethylene cylinder that he can then put samples into, like uranium ore or other neat things, pieces of silver or aluminum, and do neutron activation or neutron multiplication experiments, which is like real fission science in his house. And again, fusion is one thing. Fission, I caution you, is a totally other thing.
Where does this man live?
In Los Alamos.
Okay, cool.
Yeah. So what Carl does actually is he has a high purity germanium detector, and so he'll activate like a piece of silver, and then is able to do spectroscopy on it and see all of the elemental analysis, which is pretty neat. And neutron multiplication sort of follows into the same category, but fusion is kind of the most friendly of all of these for an amateur experimenter, because what you're doing is not going to produce any harmful radionuclides as a result. Some of those other things you're not likely to, but there's potential there for making harmful things. Also, most people know of the radioactive Boy Scout, or the nuclear Boy Scout, David Hahn, I think his name was, who made an americium beryllium neutron source and was trying to make like a neutron multiplication fission assembly out of it. And that's pretty scary stuff. So yeah, I'll probably be talking about Fuser a little more, but now let's kind of look over some particle accelerators that are feasible for making as an amateur. What I'm actually interested in making, and what I'm hoping to make soon, is actually what's called a potential drop linear accelerator. So you have a ion source on one end, which is just something you put gas through and then have a magnetic field coupled with an electronic field or radio frequency going through and inductively coupled to whatever cavity that you're passing the gas through, and you can ionize this gas, which means it's now charged. On the other end of the tube, you either have grounded or at a very high voltage potential a target. And when that goes to a very high voltage potential, like for instance, if you're making ions out of deuterium, they're going to be positively charged. You have something on the other end of the tube that's going to be negatively charged, and then the positive things go to the negative things. And if you have enough potential drop between the two, you can get up to a fairly high energy before they impart themselves on the target. In this system here, there's a Van de Graaff generator which will compile, will basically make a very big negative charge. So you could have the target up here, or you could reverse the configuration and have sort of a different scheme. I'm interested in using a inductively coupled ion source, which I can talk about in a second, and then a target that is pulsed up to high power with a Cockcroft-Walton multiplier. But these are all things that I'll continue to talk about. Linear accelerators are really neat. Potential drop accelerators tend to take up a lot of space. Making a really big Van de Graaff generator is kind of hard to do for enthusiasts or amateurs in their garage. If you are interested, you can look up pelletrons. So a lot of national labs that were doing potential drop accelerators, a lot of them have shorter accelerators that are still in use today. There'll be these huge Van de Graaff generators called pelletrons, and they'll build them in silos. And since they're generating such high voltage, they have to take all organic matter out of the silo, so no humans are allowed in the silo, and then they backfill it with SF6, which is a insulating gas, so as to not jump huge sparks from one stage of the pelletron to others. But they can usually get up to a few million volts with these pelletron systems. Not exactly feasible for an amateur to build, but to save space, there are now radio frequency linear accelerators which have these resonant cavities inside of a huge long tube, and basically the way they operate is they have a high energy electric source that is pulsing back and forth between polarities, and then you have a system of drift tubes inside of the whole tube itself that the particle sort of skips between. There are some really complicated maths in designing this though, because as the particle is traveling faster, your drift tubes sort of have to get longer as you go down the entire accelerator. This is something that an amateur could feasibly do. RF power is black magic. I haven't really had a huge grasp of it yet, so this is not something that I'm willing to try just yet. And this is something, of course, in particle physics or experimental physics or radio frequency power would probably be handy before designing. So, but really neat nonetheless. Cyclotrons, I would posit, are probably the best way that an amateur can build something very high energy in their garage, decently easy. So the way cyclotrons work is kind of clever. Back in the day when they were doing linear accelerators, they thought, okay, well, the accelerator is going to have to get longer and longer for us to get to higher and higher particle energies. So instead, what we can do is basically magnetic fields can be used to bend ion beams. So if you have a circular chamber that starts out as an ion source in the center that spits ions out in straight lines, you then take big magnets, and those magnets can be used to circulate that ion beam in circles over and over and over again. So you basically have a linear accelerator just with two big magnets around it that makes the beam recirculate pretty much as many times as you want. It just depends on how strong your magnets are. So building the vacuum systems for this is decently easy. You only need a few thousand volts for ionizing your gas. You do have to have a RF power supply for this, but most ham radio equipment, so a signal generator and some amplifiers, would be capable of getting you into the same RF power that you would need to switch polarity of what are called the Ds inside of the chamber, which is a D-shaped electrode that changes potential to encourage the ion from one side of the chamber to another. These systems for an amateur could foreseeably get up to about 1 million electron volt in particle energy, which is incredibly high. I mean, you're getting into ranges that national labs and universities are using for particle physics experiments, and the potential of having this in your garage is insane. With that, you have all sorts of interesting radioactive effects. Not necessarily radioactive effects, but you're going to generate a lot of X-rays in the system just because of how high energy your particles are, and if they're going to hit anything else, for instance the chamber or any stray particles of air that might be in the chamber, when they slow down they're going to generate brainstorm X-rays, which are fairly easy to shield, but you have to kind of be aware of that when you're designing it. So when you're designing a cyclotron, some of the things, this is another thing I've been interested in quite a while, and you'll note earlier I said the cyclotron was using a 2 Tesla magnetic field, which is comparable field strength to what an MRI is putting out. So how do you get that in your garage? I guess you could find an MRI, but it's not really the form factor that you need. So I've actually looked at, okay, how big and how strong can I buy rare earth magnets, neodymium magnets, and are they feasible to use to build a permanent magnet-based cyclotron? And I found that if you have maybe a grand laying around, you can actually buy these really, really huge 6-inch diameter by 2-inch thick neodymium magnets that, if placed in a yoke, which is kind of like a Ferris square, so you put one magnet up top and one magnet on the bottom, so they're pushing against the borders of the square. You generate a magnetic field in the center that can be somewhere between 1 Tesla and 2 Tesla, depending on how far the faces of the pole are away from each other. And there's some basic math that you can do to determine, okay, I have these 2 magnets, I have this yoke, this is the size, and this is how far away they are from each other, and determine what kind of field strength that you're in. So now I'm basically waiting until I can save up enough money that I can reasonably justify buying magnets for almost $1,000, which is tricky to convince yourself to do. So donations are encouraged if you are so predisposed to do so. But here are some neat pictures that...
Shut up and take my money.
Yes, gladly. So these are a couple of cyclotron examples. The one on the right was actually one of the first cyclotrons ever made, and it's stupid simple. They've got basically epoxy everywhere. I mean, this is something that you or I could build in our garage with components that were bought at Home Depot. The magnet up top was actually wound by high school students. They have a website called Cyclotron Kids. Now, two of them are at Caltech and one of them is at MIT. Actually, does anyone here ever heard of One Tesla, the Kickstarter project, the Tesla coil that was... Okay, anyways, Heidi, the girl who made One Tesla and who's running One Tesla now, was one of the cyclotron kids. But they ended up making a cyclotron while they were in high school, which is just incredible. And it shows that if a couple of high school students can do it, you can do it as well. These two pictures on the bottom are actually of an ion source, so you can see that the gas is coming in back here, and then there is a extraction electrode, let's call it. So a gap right here where the ions are actually coming out into the main chamber and get circulated around. Again, like super pretty stuff. The fact that you're putting gas in and then you're transforming it into a beam of ions that's then getting circulated in a particle accelerator is just mind-blowing to me. So now I'm going to sort of go into, so you want to build an apparatus, what do you need? And I'm going to try to be as brief as possible, but again, this is my attempt at condensing everything that I've learned in like the past year to matter that anyone who's interested might be able to walk away from this talk and then start designing their own system. So there are a couple of things you're going to need. That would be high voltage, a vacuum, some detectors, vacuum chambers, and the hardest thing for me with my fusion project has been generating a very, very high vacuum in my garage on a very tight budget. So my system for the fuser is two vacuum pumps. I have a roughing pump and then a high vacuum pump. And I've gone through several different vacuum pumps to get to where I am today, but essentially you'll need a vacuum gauge. I have what is called a Pyrani gauge. I bought it off of a fellow Georgia Tech student for $30 and then found the documentation and wrote a program for an Arduino that takes the nonlinear analog output and then converts it into pressure. So if you are able to be resourceful with some electronics and prototyping, you can usually buy things from eBay that are really, really cheap, write something simple for an Arduino and throw it on a breadboard and then you're good to go. So you can often get things cheap if you are able to do some research behind them. Then I have a two-stage belt-driven piston-style pump called a Welch 1400, and then a diffusion pump. And I've kind of become obsessed and enthralled by high-pressure vacuum pumps because they are very aggravating, so I have like a love-hate relationship with them, kind of like Stockholm syndrome, I guess. But they're usually pretty elegant in how they operate and again, kind of pretty to look at. So the pump on the left here is what's called a turbomolecular pump, which has, I'm too lazy to count how many stages this one has, but usually 5 to 12 stages of turbines that have increasing pitch as you go from the top to the bottom, with usually a brushless 3-phase DC motor in the bottom. It spins all of these blades up to supersonic velocities. This is backed by a roughing pump, so you don't start this up until you're already at some level of vacuum pressure, which allows these blades to spin so fast with very little friction, so because you're not passing that much gas through them. So these, though, are quite expensive. The brushless motors can require expensive controllers. A while back, we found a series of this pump that was being liquidated from a national lab for $90 on eBay. And one of the people in the Fuser website had posted a schematic to DIY this controller. So for $150, you could have a whole turbo pump system with the controller. And I used that for a while and then traded it for the current pump that I have, which is an oil diffusion pump. So essentially, it's dead simple. You have a heater at the bottom of the pump, you have some oil on the inside of the pump, and then what we call a Christmas tree. So as the oil boils, it creates vapor, goes up into this assembly in the center of the pump, and then as it goes up, it hits these baffles which direct it back down, and it will shoot down at supersonic velocities and drag everything in the chamber attached to it into the roughing pump. So the pump on the far right is what I actually have in the other room on my fuser, and we can go in there after the presentation and talk about all the stuff I have if you're interested. As I said earlier, high voltage is kind of paramount in high energy physics. I was lucky enough to find a regulated DC high voltage lab power supply, which basically has a 6.5 kilovolt transformer coupled with a Cockcroft-Walton multiplier stack, which will go up to 50,000 volts. And you can actually build that at home for not too difficult. You can get neon sign transformers, put them in parallel with each other so as to get a little more current out of them, and then put a Cockcroft-Walton stack in front of them. So basically get a Home Depot bucket and fill it up with mineral oil, go on to Mouser and buy a bunch of diodes and capacitors and put them all together in a Cockcroft-Walton configuration, which is easily found on Wikipedia or just about anywhere else from Google, and get up to just about as much voltage as you want, so far as your components are rated up to that voltage. Otherwise, they will burn out. So generally, once you start getting into accelerator design, though, you need an ion source, which is, again, something that you put the gas through to ionize it before you're able to do really anything useful with it. So some ion sources have a low voltage filament, kind of like a light bulb, that will thermionically emit electrons that can then be used to ionize things. This is a 12 volt or typically somewhere around there DC supply, which can be fabricated with components from Radio Shack and a cheap transformer that you can scavenge out of just about anything. Then the high voltage extraction source, like in the cyclotron picture that I showed you, the extraction electrode, is usually a little bit higher of a voltage power supply, but we can usually use a neon sign transformer with a rectifier on the end of it to do that. With accelerators, you're going to need some sort of RF power supply. I already mentioned that you can use ham radio components for this, a signal generator and some amplifiers, or amplifiers that you can find on eBay. Van de Graaff generators are not that hard to construct. There are tons of instructables and guides on Google on how to do those, or you can just use a lab power supply like I am. For particle accelerators, this is going to severely limit what you can actually do. 50,000 volts is kind of small for a potential drop accelerator, but it's enough to get you started. So also something I didn't mention yet is X-ray transformers can also be utilized. Sometimes you can find like dentists or chiropractors who are throwing out their old X-ray transformers, and they're a lot of fun if you can get your hands on one. Caution is encouraged though, because usually these are submerged in oil and in this huge steel container that usually weighs like altogether 500 pounds or so. So you're going to need a lot of friends that are encouraged to help you to get this in the back of the truck and then into your garage afterwards. If you're very interested in an X-ray transformer, there is one sitting in a scrapyard in Atlanta right now that I can give you the location of that they're willing to sell for $150, which is a huge bargain. I haven't bought it yet, but I'm hoping someone will, and then I might be able to play with it.
Is this where the donations come in?
Yeah. So help me buy an X-ray transformer and help me move it. Detection equipment is very important because if you're going to be generating radionuclides or charged particles that have the potential to emit X-rays or other fun things or neutrons, you're going to want to have some equipment to tell you that that's actually happening. And especially when you get to like wanting to publish work or things like that. We have a policy on the forum now that you have to list certain information and you have to show how you've calibrated your detectors before we actually recognize your claim that you've achieved fusion. So this is very important, and I would pretty much encourage anyone who's getting interested in these projects to not budget on, not try to penny pinch with this. It's very important that you get stuff that will allow you to operate safely. And this may be a good investment to start out with, because even if you don't end up building your particle accelerator or fusion reactor, you can still take your Geiger counter down to the flea market or antiques store and find uranium plates or Fiesta ware and things like that. So they're pretty cool to have around. So at the very minimum, you want to get a Geiger counter, which which with all of the preppers around these days and apocalypse people, they're pretty common on eBay. You can buy the old civil defense Geiger counters for 20 to 30 bucks sometimes if you catch them on eBay. There are also other really neat devices made by Loveland. One of them is called a Model 12, and it's basically a detector unit that you can plug just about any kind of detection tube into. I have sort of the bigger brother that's made sort of like a rack-mounted unit that's called a Model 2000, and it has all of the preamp, the amplifier, the scaler, and the counter all in one box. And again, you can plug a Geiger tube into this, you can plug some sort of tube to detect neutrons or a photomultiplier tube, all sorts of things all in one unit. There are also what I call nuclear detector Legos called NIM bins. You can buy like a rack and then just slot these bins into them and have one for a preamp and one for an amplifier and one for a single channel analyzer. And often these can be found in places like the Black Hole. If you ever find yourself in Los Alamos, there's a scrapyard for Los Alamos National Lab called the Black Hole. And they have all sorts of nuclear electronics and vacuum chambers and dewars for cryogenic liquids and lots of fun stuff. And they've got a huge pile of NIM bins laying around that they sell for really cheap. So as far as the actual tubes, so you have a counter and an amplifier and all of that, and then you have a tube to go along with it. So Geiger tubes are really cheap on eBay. You can find them just about anywhere. There are also a surprisingly large amount of like Arduino-based Geiger counters now. I think Adafruit actually has a kit you can buy for I think under $100, which comes with a little Geiger tube, which is pretty neat. And it will serve you for basic things like detecting if something's producing X-rays, or if you've found a piece of Fiestaware, or how hot your piece of uranium is that you found, or something like that. Proportional tubes sort of get into things like detecting specific particles like neutrons. I have both a B10 tube and a BF3 tube, which basically you put behind a moderator. That's a material that slows neutrons down. When neutrons go through the moderator and then into the tube, they make an electrical pulse that you can then detect. And this is really what tells you if fusion is happening in a reactor. If you're getting electrical pulses from these tubes, you know neutrons are happening, which is pretty great. But this is kind of paramount to have if you're wanting to do fusion and prove that you're doing it. Scintillation detectors and solid-state detectors are also very cool devices, but scintillation detectors can get pretty expensive pretty fast. And solid-state detectors are actually neat. There are a bunch of people who have taken like little photoelectric cells or small solar cells and found out that if you take like some of the face coating off of them, you can put them in a light shielding container, and they will actually detect charged particles like X-rays or gamma rays. So, and those can be made for like $5 or $10 using components from the Mouser. So far what I've designed is a beam-on-target system because I'm too cheap to buy magnets. It will be a deuterium beam-on-target linear accelerator. Currently I've made a nice ion source. I'm working on a titanium target right now, and then I'll be moving on into the future for an inductively coupled RF ion source, which is basically you take a glass tube and then you have an antenna wrapped around it, and then you have a radio frequency power supply that you can then use to energize that tube, which has gas flowing through it, and you can ionize it by using that. And you have an extraction electrode below it, and you can pull the beam out. Then I'm also going to construct a target feed-through, which will allow me to get up into the hundreds of thousands of volts, which will be exciting. So these are some pictures of what I've done so far. This is my magnetron ion source, which basically works similar to like a magnetron in a microwave. You have a magnet in the center. So this right here is a neodymium magnet. And like I was talking about earlier, magnetic fields can bend ion beams. So what this does is essentially, once you have some ions happening in here, so gas comes through, this little coil here is heated up with low voltage, so it starts glowing. Thermionically emits electrons, and then when gas flies past those electrons, which are circling here, it gets ionized, and this ring on the outside is the extraction electrode. So you end up getting ions flowing from the front of this device, and you end up getting this neat-looking plasma halo from the ion source. This is a picture of it in operation. which looks really neat, and it's a pretty cool beam, but it's not a very focused beam. So with a magnetron ion source, you end up having to do some electrostatic lensing or magnetic lensing down on the line. So that's why I'll be switching to an inductively coupled RF source. So these are some more pictures of construction. I turned this on a lathe, and I was kind of proud of it because it held the magnet into the next lead. And so as far as beam on target stuff, I've had a leak for quite a while, and all of these pressures are really high, like close to atmospheric pressure. So you'll notice here I kind of have like a standing wave in the plasma because I'm not at a low enough vacuum pressure to remove all of the other junk charge carrier particles from the system. But it looks pretty neat. The ion source is over here, and the target is on the other side of the chamber. I can start ionization on this side and direct those particles to the target. So in theory, it's kind of operating just not at as high energies as I would prefer it to. This is another picture of the ion source, not as low pressure as what I displayed earlier. This is a shot looking at the beam coming out of the ion source. And these are some useful resources that I have, or I would suggest people look into if you're going to be building an apparatus like this. Again, if you scan the QR code at the first of the presentation, these things will be available to you. Cyclotrons.net is a forum of people who have built cyclotrons before or are in the process of building them. Really neat people there who are always really open to help, and the same thing goes with Fuser.net, a bunch of people like myself who have built fusers before and are around on this forum to help other people out with building their own or doing collaborative experiments. So with that being said, any questions? Also, like I mentioned earlier, we can go over to the other room where I have the fuser and go through a component by component basis and maybe start it up if you guys are interested. As I mentioned earlier, actually I've been making a new stand for the reactor, and in the process of mounting it, I over-tightened some bolts and actually put a crack in my glass viewport, so it's not holding vacuum very well, and I don't have a part to repair it in Tennessee, but kind of just goes to show that transporting a nuclear apparatus from Georgia to Tennessee is kind of a difficult thing. But we can go through it and kind of start it up and do a bit of a demo if you guys are interested. Otherwise, thank you for coming. I'm glad you all sat through and listened to me.